Okay, welcome again to our journey into number theory. I'm going to look at the exercises for chapter 2, section 2. And we're just going to do 2 of these, but the first one's got quite a lot of steps in it. And it provides another proof for this result that we proved before. In fact, we'll see lots of proofs of this as we go through. But here's another proof, a more analytic one really, bare hands one, for the fact that the sum of the reciprocals of the primes diverges. And we're going to do it as follows. We're going to suppose the contrary, then that means the tail of the series is eventually small. So we can go far enough along the series so that the sum of the tail is less than a half. Now we're going to let, and that's going to happen after the kth prime. So I'm going to let Q be the primes, the product of the primes up to there, P1 up to Pk, and we're going to consider numbers of this form, 1 plus NQ, where n is 1, 2, 3, and so on. We're going to show that this sum diverges. We're going to explain why every prime factor of this denominator here has to be bigger than this pk plus 1. Remember, that's the point where we started calculating the tail. We're going to then take this sum, I've called it S sub r, this finite sum, and we're going to show it's less than this sum. And then we're going to deduce that this S sub r is less than 1, and that will contradict the fact that this thing diverges. So here is the full worked solution for this one. So we're going, as I said, we're going to suppose that this thing converges, then the tail can be bounded, provided we go far enough, that there is a k, so that this sum is less than a half, where Pm is the nth prime. We put Q to be the product of these primes, up P1 up to Pk. Well, firstly, the first bit's trivial here. This thing diverges immediately by the integral test. If we just integrate 1 over 1 plus Qx from 1 to infinity, then this is a logarithm, and so it diverges to infinity by the integral test. Nothing to do there. 1 plus NQ. NQ, remember, is the Q is the product of all the primes P1 up to Pk, and so each prime factor of this, it can't have any of the P1s up to Pk's as prime factors, because it's mod 1. It's modulo any of those primes, the residue is 1. So any prime factor has to be bigger than Pk plus 1, so that's fairly obvious. Now, for the slightly more difficult bit here, we let SR be the partial sums of this 1 over 1 plus NQ. And we were asked to look at this sum here, which is t equals 1 to infinity of the sum of this sum. So this is the m equals k plus 1 onwards. We were given in the question that this was the sum up to infinity, which I'm going to put in here. And then this all raised to the power k. So this was given to us. We had to show that this one is bigger than the S sub r that we had above. Well, I simply write this out. So this, we put t as 1 in, then writing this sum, I get 1 over pk plus 1 plus pk plus 2 and so on forever. And then plus, I put t equals 2 in, I get this, and so on. Dot, dot, dot. Now, this is the sum of the reciprocals of every, when you expand this out, you're going to get the sum of the reciprocals of every integer with prime factors bigger than bk plus 1, just by the fundamental theorem of arithmetic. So you're going to get every number which has prime factors which are bigger than or equal to pk plus 1, and you're going to get the sum of the reciprocals of all of these. So that means then that sum we had S sub r is in fact, will contain all of the terms in here. So this S sub r is less than this sum that we had here, an infinity there. Now, by assumption, then, this SR is less or equal to t equals 1 to infinity 1/2, because we assumed that this sum here was less the tail of this of the sum of the reciprocals of the primes. We assumed that this was less than 1/2, so this is less than 1/2 to the t, and this is just a geometric series, and so it adds up to 1. And finally then, that tells me that this S sub r now has bounded partial sums, but that contradicts part A, where we said that this sum in fact diverges. And the conclusion is then that the sum of the reciprocals of the primes diverges. So that's an alternate proof to the one we did in the other lecture. There are many proofs of this fact. We'll see this a bit later on. It will follow fairly easily once we have the Riemann zeta function and the Euler product. We'll see this, we can deduce that from that as well. And we'll see also we can get this from the prime number theorem. The second question in this for this section was just a little bit of fun here, really, to evaluate these two sums. So where we let A denote all the integers of the form 2 to the r, 3 to the s, 5 to the t. So all integers that have 2s, 3s or 5s only as the only prime factors. Now of course the r, s or t could be 0 as well. And we want to know what the sum of 1 over n is for numbers of this form, and the sum of the squares for n in this set. And this is quite a nice little exercise to do, actually. So if A consists then of all the numbers of this form, where r, s and t are non-negative integers, they could be 0, then this sum then we'll get by taking, again using the fundamental theorem of arithmetic, using this Euler product idea. Well, it's going to be it could contain 1 plus 2 plus a quarter and so on, or 1 plus a third plus a ninth and so on, or 1 plus a fifth and so on. And then we can multiply all these brackets together, and when you expand all this out, you will get exactly this. You'll get the sum of the reciprocals of all the numbers whose only prime factors are 2, 3 and 5. Now the point is, this again is a nice geometric series. I can sum that one. This is a geometric series. I can sum it, geometric series. And I can simplify this and we get 15 over 9, which is a nice solution here to the problem. So that's the value of the sum. Once you've seen that idea, part B is identical really, except now you just replace the primes with 2, for example, with 2 squared, 2 to the 4th and so on, 3 with 3 squared, 3 to the 4th and so on, same with 5. And again, these are geometric series, so we get 1 over 1 minus a quarter, 1 over 1 minus a ninth and so on. And when you simplify this thing, you get 25 on 26. You might like to try it for including perhaps the prime 7 to see what happens if you do numbers of the form 2 to the r, 3 to the r, 3 to the s, 5 to the t and 7 to the u, and see what the corresponding sums are there as well. And they're the tutorial problems for section 5, section 2.2.